Okay, let's begin. So, last class was a bit of a whirlwind, so let's make sure that we took away from that what we were supposed to. Let's go through some of the rules. Define. Yes.
The limit with h goes to 0 of f(x) plus h minus f(x) over h.
Okay. Tell me what the chain rule says.
dx of f of g of x equals f prime of g of x times g prime of x.
Tell me what the product rule says.
F of x times g of x, or ddx of that f of x times g of x equals f prime x times gx plus g prime x times f of x.
And the quotient rule? Maybe someone else? Yeah, Suki?
F prime G. Yeah,
Where? What?
for quotient, you can do F prime G of F prime of X times Gx.
Well, the quotient rule is an equation.
Yeah. So I meant it that way, like as an equation. Or, okay, never mind.
Well,
Never mind. I'm a little confused.
so it's quotient rule, it starts with a ddx.
Yeah.
So that's literally the first thing you need to say. Did you?
ddx f over g equals f prime g minus g prime f divided by g squared.
What about the power rule? What does that say? Yeah.
ddx of x to the n equals n times x to the power n minus 1 to the n.
How would you differentiate e to some function?
U prime times e to z.
How would you differentiate the natural log of some function? Did you?
G prime over
How would you differentiate a to the x? Yeah, Diego?
ln of a
Yes, ln of a. What about if I ask you a to the u?
ln of a to the x x prime or u prime.
It's u prime a to the u ln of a. What is the derivative of the sine of x function? What is the derivative of the cosine function? Kind of. Sine. There is something I forgot to derive for you guys last time. I didn't put it on the quiz, well, not on the official part, as I remembered that I didn't remind you guys. But to find the derivative of a general logarithm, like log to the base of x. Did anyone figure that out or know what that was? Yeah?
1 over x, 1 over a ln it, or 1 over x ln it.
X ln a. Right. So now I never derived that for you, so I didn't put it on the quiz. But the derivation would be by the change of base formula. So the idea is here, log to the base a of x, you could actually rewrite that as ln of x divided by ln of a. And that's by applying the change of base formula. And now your ln of a is just a constant, so you can differentiate. Right? So this is just 1 over ln of a the derivative of 1 over ln of a times ln of x. We know how to differentiate ln of x. This is 1 over x. So it's 1 over ln a times 1 over x. So you get 1 over x ln a. And I tend to write the ln in the back because I don't want students to get confused with, if they put the a to the x on the back, that the ln is logging everything. It's only logging this part. It's only logging the constant. So that would have been the formula here. What else did we talk about? What if we had to differentiate f of x plus g of x?
F prime of x plus g prime.
Well, what if I replace that with multiplication, and then what? Yeah?
F prime of x times g of x plus f of
Right, it's
x.
the product rule.
Yeah.
I wanted to see if you guys just distribute it across the product. Okay. Right, so the product rule. So this is still f prime times g plus f times g prime. By the way, just a pro tip here, the product rule can be extended in a pretty natural way. The idea is you have a sum of terms where everyone in the product gets to be the derivative once. So for example, if I wanted to differentiate a product of 3 things, f, g, and h. So in one case, f gets to be the derivative, everyone else gets to be the same. Then g gets to be the derivative, everyone else is the same. Then h gets to be the derivative, everyone else is the same. Right? So you can kind of extend this that way. Now you could prove this by applying the 1 and 2, just by thinking of g of x as a function, then using the product rule and expanding, but you'll ultimately end up with something like that. Or if you look at 4 things, it's going to be similar. F gets to be the derivative, everyone else the same. G derivative, everyone else the same. H gets to be the derivative, everyone else the same. And then I gets to be a derivative. And then of course, etc. You can keep expanding the product rule in this very natural way. Right? You pretty much just keep the product. You copy it down as many times as there are factors in that product. And then each factor gets to be the derivative in one part of the sum. Just a little pro tip there. So you don't really have to apply the product rule in pairs. You can actually extend it pretty naturally. So we're going to get, you guys already did a quiz on this, but we're going to spend this class getting a little bit more used to the derivative, doing a few more examples, and then we'll talk about the existence of the derivative, and we'll end there. And next time we will talk about, I think higher derivatives and implicit differentiation would be a nice thing to do next time. But let's derive some other important ones. For example, the other trig functions. We know how to differentiate sine and cosine. How would you differentiate tangent? Yeah.
Would it just be sine over cosine?
Well,
Sine
the
x over-
derivative of sine x over cosine x, right? So you didn't take the derivative yet, you just pretty much rewrote tangent, and then what?
You find the derivative for each and use the quotient rule.
So you can use the quotient rule because we have f over g, and so what would that look like?
Like cosine squared of x minus sine squared of x over something or other.
No, you're going too fast. Just write it out piece by piece according to the formula.
Would it be cosine of x times sine of x minus negative sine of x times cosine of x over cosine of x squared.
No, you're not using the formula, Todd. Yeah.
Cosine x times cosine x.
All right, it's the bottom times the derivative of the top minus
Minus sine x times negative sine x
the top times the derivative of the bottom
over cosine of
over the
x.
bottom squared. Now, paying attention to that, we'll realize the negative times the negative will give us a positive. So here I have cosine squared plus sine squared of x. And what does that give us? Cosine squared x plus sine squared x?
1.
It's 1. So we just get 1 over cosine squared x. Is there a nice way to write that? Secant squared. So it turns out that the derivative of the tangent x function is secant squared x. And of course, remember, in every basic derivative rule I give you, there is going to be a chain rule hidden in there. So basically, if I want to differentiate tangent of any function, it will be u prime times secant squared of that function. So that's the chain rule version of this. What about the secant? How do you differentiate the secant function? Yeah.
So negative tans x.
How'd you get that?
Oh, because I took calculus here.
Okay, for the benefit of us who didn't take calculus here, how would you figure it out? I mean, as of now, this is something you should remember, but I want us to derive it the first time, and then we'll remember it every, yeah?
I'm not sure, but we can rewrite it as 1 over cosine x. And I have a question here.
Well, you could apply the quotient rule. I think it's a bit of an overkill here, though.
Yeah, we can just take the derivative.
You can take the derivative of what? Yeah?
You can rewrite it as cos x, and you get 1, and then do the chain rule.
So I would do that, and then apply the chain rule. So the chain rule would give us what?
Negative 1 over, or negative 1 over cos, 1 over negative cos squared x times
Well,
negative
I
sine
just do this and subtract 1 from the power. Yeah?
times negative sine squared x.
Times the derivative of the inside minus sine of x. So that gives us 1 over cosine squared times the sine. And to write that a little bit nicer, we can leave one of the cosines here, slide it under the sine, slide one of them under the sine. And this will give us tangent, and this will give us secant. And so it's not, there's no negative sign there. Positive secant times tangent. So the derivative of secant is secant x tangent x. Of course, this implies that derivative of secant of some function is equal to the derivative of that function times the secant of that function times the tangent of that function. Similarly, not going to derive the others, but you probably should. It would be nice practice. You can differentiate the cosecant function. This one, these have the negative signs, minus cosecant x cotangent x. And you can derive the cotangent function. This is minus cosecant squared x. So these we by similar things. Like write this as 1 over sine. I do the chain rule and write this one as cosine over sine and do the quotient rule, and you will be able to simplify to those. So that's the derivative. Now we know how to differentiate all the elementary trig functions. Sine, cosine, tangent, cotangent, cosecant, and secant. We'll talk about a couple of the inverse trig functions later, maybe 2 lectures from now. But yeah. Let's do some more examples. Yes, all the rules that we started off with and everything I put in a box just now, these are things that we should just know now. You shouldn't have to look in your textbook to come up with these rules. We should be able to just regurgitate them at will relatively quickly. Well, let's do some more examples here. Let's look at this here. Let's do those. Just a few random examples here to know that we are applying the rules properly. Efficiently. How about the first one? How do you differentiate that? Second copies. Okay, what rule would you use here? Quotient, okay, how would you apply it?
Cosine of x times x minus sine x over x squared.
So it's the bottom times the derivative of the top minus the top times the derivative of the bottom, which is 1 over x squared. Yeah, quotient rule. Nothing really to simplify there, so let's just move on. B. How would you do this one? What rule would we apply? Yeah.
Oh wait, no, yeah, it would be. Yeah, it would just be quotient
quotient rule again, or division of functions. Okay, so
So x plus 2 times 2 is minus x plus 1. Or would you have to change? Sorry. Would you need to change in this case? No, right?
we would need to what?
No, sorry, I'm just thinking out loud. It would just be x plus 2 minus x plus 1 over x plus 2 squared,
Right,
right?
so it's bottom times derivative of the top, which is 1, minus the top times the derivative of the bottom, which is also 1, all over the bottom squared. And so here we have x minus x, we have 2 minus 1, just have 1 over x plus 2 squared. C, how would you differentiate x squared over 2? Yeah.
If you use the constant factor rule, you can pull out the 1/2 and just take the derivative of x squared. So it'll be
Right.
1/2 times 2x.
Right, so you just differentiate the top, leave the bottom alone. So that's just x. Right? You can apply the constant factor rule here. Just want to make sure that we're all aware of that. Note, x squared over 2 is just 1/2 times x squared. So we can apply constant factor rule. And this gives me an excuse to point out that just because you have a division doesn't mean you, as a knee-jerk reaction, you go to the quotient rule. Sometimes it's overkill, and so let's say quotient rule is overkill here. And usually, with a problem like this, when someone tries to apply the quotient rule, they'll often forget that the derivative of 2 is 0 for some reason, and end up getting it wrong. So you don't need, if denominator is constant, you essentially just leave the denominator alone and differentiate the numerator. Not a terribly difficult problem, but I just wanted to point out, if your denominator is a constant, you're wasting time with the quotient rule, and probably causing yourself to make mistakes that you otherwise wouldn't make. So don't do it. What about D? This is also a division. What do we do here? Yeah.
Or would you use the constant factor rule on number 3 and then use the power rule on the radical x?
How would you apply the power rule?
So,
Like you leave the 3 alone and then do the power rule in the denominator?
so you make it ddx equals, or ddx equals 3 times x to the power of negative 1/2. And then you take the 3 out and find the derivative of x to the negative 1/2, which is
Okay. And the derivative of that?
negative 1/2 times x to the power of negative 32 and times 3.
Right. And a similar thing applies here, as I did over here. And we actually used it earlier today when we were looking at the secant. We saw 1 over cosine. Instead of doing the quotient rule there, we simply just brought it up and applied the chain rule. And so, again, it turns out if the numerator is a constant, don't do quotient rule. It's not that it would be wrong, it's just it's not recommended to use it here. just rewrite using the laws of exponents, which tells you I can just bring it up and make the power negative. And use the chain rule. So just a pro tip there, if you have a division and either the denominator or the numerator is a constant, I wouldn't go with the quotient rule. It's just overkill and it'll just cause you a lot more writing, and you writing down more stuff will give you more opportunities to make mistakes. So yeah, for these guys, at just face value, it looks like you'd use the quotient rule with them, but I wouldn't because of the constants. Now let's look at, I'll probably need more space for E, so let me just erase this one. Okay, what about E? Yeah.
Use the chain rule to find the derivatives of each of the two terms, and then use the product rule
Okay.
to multiply the derivatives into terms themselves.
So we can see here, there's a product. We have this times that. This is like your F. This is like your G. So we really have a product of two things, but then we start to look individually at the F, and that's just something raised to an 8th power, which I wouldn't want expanding. So I would use the chain rule whenever I need to differentiate that, and I would use the chain rule whenever I need to differentiate that. So how would that be applied here?
It would be 8 times 2x plus 1 to the power of 7 times 2 times x squared plus 1 plus 5.
To the 5th.
Oh yeah, sorry. Plus 5 times x squared plus 1 to the 4th times 2x times 2x plus 1 to the 8th.
Times 2x plus 1 to the 8th. So that is just us applying the product rule. Here this is your F prime, here this is your G, here this is your F, and here this is your G prime. Okay, simplify. Yeah.
You could pull out a 2 and then 2x plus 1 to the 7th and then x squared plus 1 to the 4th.
So when you want to simplify something like that, usually it will mean factor. You'll notice that 2 is a common term, so I can pull that out. I would also notice that 2x plus 1 is a common term. That appears to the 7th power and the 8th power. You always factor out the lowest power, so we'll factor out the 7th. And we have x squared plus 1 is a common term. That appears to the 5th power and the 4th power. You always factor out the lowest power, hence we factor out the 4th power. Open up the parentheses, what do we have left inside? Yeah. What's left over? Yeah?
8 times x squared plus 1 plus 5x times 2x plus 1.
We already have that left over. Now, intermediately we can say, okay, this is 8x squared plus 8. This is 10x squared plus 5x. And so we can actually just combine those. So this would be 2 times 2x plus 1 to the 7th, x squared plus 1 to the 4th, times 8x squared plus 10x squared, 18x squared plus 5x plus 8. So a little bit of algebra there, but sometimes it's necessary. We will see in the coming days that sometimes we want to be able to determine where the derivative is 0. So if we had an expression like this and we want to know what x values makes that 0, you would need to factor it and then use the zero factor property to determine the solution to such an equation. So knowing how to simplify the derivative after taking it is also a very important skill. How would you do that one? Yes. Quotient rule. Same functions involved, except they're now being divided instead of being multiplied. Now you might recall, we actually proved the quotient rule from the product rule. So you do have the option of doing something like moving the thing up here, bringing it up and making it the -5 power and doing the product rule. At this point, that's a matter of personal preference. I don't particularly think it gives you any advantage when it comes to the amount of things you have to write down, because usually if you apply the product rule, as you can see, it gives you 2 terms, where a simplified version, it has 1 term. And so the quotient rule actually just gives you in 1 term pretty much after you factor the numerator. So anytime you save by using the product rule, you'll probably lose it by having to combine the fractions at the end. So it's up to you, but I'd probably just stick with the quotient rule interpretation for something like this. But that's not a strong recommendation. If you saw it first and move the bottom up and use the product rule, that's fine. So what we would do here is, again, we know the quotient rule, so it's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. What is the denominator squared here?
X squared plus 1 whole to the 10.
To the 10. Right? When you square it, you multiply the powers. One of them, make sure of that. Every now and then I see students squaring the 5 and making it 25. No. You want to square something like that, this squared, laws of exponents says you multiply the powers, you actually double the power when you square something. Okay, so that's over the 10th. Now, we can factor pretty much in the same way that we did here. So the common term would still be two is a common factor, pull that out. 2x plus 1 to the 7th, and x squared plus 1 to the 4th. We'd open parentheses. The 2 we took out, the 8 is left. This guy to the 7th we took out. We took out 4 factors of this. There were 5, so there's 1 left. Minus, we took out the 2. There's a 5x left. 7 factors were taken out. We had 8, so there's 1 left over. And we took out everyone there. All over x squared plus 1 to the 10th. Notice that we can now simplify that to the 6th power. These guys are going to expand to be the same thing, except we're going to have a negative sign in between them now. This will be ax squared plus 8 minus 10x squared plus 5x. Well, I put the parentheses. So that simplifies to times 2x plus 1 to the 7th times 8x squared minus 10x squared minus 5x plus 8 over x 1 to the 6th. How would you do this one? Yeah.
It would be 1 over whole, and then inside part times the derivative of that would be good, which is we already saw
Right,
before.
which we just found. Let's say you didn't just find that, right? This just showed up. There's a better way to do it. Yeah.
You use the property of logarithms and subtract the 2. So it'd be the natural log of 2x plus 1 to the 8th minus the natural log of x squared plus 1 to the 5th.
So the ln of 2x plus 1 to the 8th minus ln of x squared plus 1 to the 5th. Getting the derivative of all that. We can make it even nicer. Right? What could we do here? Yeah.
Take the exponents down in front.
To move the exponents down, that's another law of logarithms. Now, if you hadn't done the quotient rule before, which you might not always have to do, usually when you have log of something complicated, you can use the laws of logarithms to help you. So this is another case in which sometimes just as a knee-jerk reaction following the rules as written, sometimes it takes a breather for you to worry about simplifying before you actually apply the rule. Or thinking, do I really need to apply the rule? So just as how quotient rule, you wouldn't really apply directly here, even though it's not legal to do it. It's just not very efficient. In the same way, applying the rule that the derivative log of a function is the derivative of the function over the thing itself is not very efficient to do this. It's much more efficient to actually use the log rules to break things down a lot easier. And at this point, you can do this with minimal algebra, right? The derivative is just going to be 8 times 2 over 2x plus 1 minus 5 times 2x over x squared plus 1. And had you done all of this and divided by that, you would have gotten this, but it would have taken a much longer time. So that's worth pointing out. And we are going to look at a technique called logarithmic differentiation where we take advantage of these particular properties. So sometimes there will be cases where there are no logarithms, but we introduce it to make our calculations a lot easier. We will talk about that in the future. Finding derivatives is important, but finding them efficiently and quickly is just as important usually. So we don't want to be wasting time that we don't have. We can simplify this a little bit. 16 over 2x plus 1 minus 10x over x squared plus 1. What about h? Yeah?
I started off by rewriting it, e to the radical 2 plus 1 to the 1/2, and then I did the product.
So you rewrote it? And then you did what?
And then I did 1, and then it's 1 over 2 radical e to the radical 2 plus 1.
1 over 2 e to the radical 2 plus 1.
Oh, like 1 all over 2, all over radical. Like the 1 in the numerator.
Oh, okay. You said 1 over 2 radical.
E to the radical 2 plus 1.
Okay.
Times 2 times e to the radical 2 times x cubed plus radical e to the radical 2 plus 1 times 3x squared. Is that right?
No.
Damn it.
When it happens, it happens. What's the issue here? Yeah.
The radical e to the radical 2 plus 1 isn't a function, so you can just treat it as a constant.
It's a constant. How do you know it's a constant?
There's no x.
There's no
no
x.
variable.
X is our variable, and we only have numbers here. E is a number, radical 2 is a number, 1 is a number. Take the square root of that, you get a number. This is just a constant times x cubed. Even if you were going to do this, I don't think rewriting there was really any point to it here, but the trick was to notice this is a constant. And here's the thing. Technically, it's not illegal to do this, but this kind of illustrates what I'm saying. When things get too complicated, it's hard for your brain to like keep things straight. Even if you were to do this, this wouldn't be wrong. How would you actually fix this step? Let's say someone went and tried to do all of this. This part would be 0. And so you would literally wipe out that first term anyway, so you know, oh, product rule is probably over to that point. But that's what I'm saying. Usually people don't remember that, right? So, I mean, it was obvious here because the number, it was just a 2. It wasn't scary, it didn't look very complicated, right? So someone could get away with applying the quotient rule here and they were, oh, derivative 2 is 0, but sometimes they don't, right? So even if you're applying this overkill kind of thing, a lot of times people forget that you'd have to apply the 0. But it's much easier to just recognize that's a constant, and so the constant factor rule applies. So you just leave that alone and differentiate the x cubed.
Is it x squared?
That's the x squared. I said x cubed, that's what I was writing. Yes, that is 3x squared. So be careful with that. This is what it means to be careful when you're applying a rule, because usually when things start getting big and complicated, it's hard to keep things straight. You should always know what kind of thing you're looking at. And that huge thing right there is just a constant. So we'll stop there. I'll see you guys on Friday.